We learned in our last lecture that a zero of a polynomial function is basically a complex number that once plugged into the function results in 0 as the output. Now, an important theorem connected to that is the factor theorem, which says for any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. This IFF is not a misspelling. It actually means if and only if. We use it very often in mathematics. What that means is this is a biconditional. So x minus k being a factor of a polynomial implies that f of k equals 0, as well as f of k being 0 implies that x minus k is a factor of the polynomial. So it's a biconditional. Now we can prove this actually quite quickly. Suppose that x minus k is a factor of f of x. Then there exists a polynomial q of x such that f of x equals x minus k times q of x. That's just what being a factor means, right? Now, if you calculate f of k by plugging k in here instead of x, we end up with f of k equals k minus k, quantity k minus k times q of 0, which is of course going to be 0 because k minus k is 0, and regardless of what q of 0 is, the output is going to be 0. Now, let's go the other way. Now suppose that f of k is 0. Now we know from the remainder theorem that there exists a unique polynomial q of x such that f of x is going to be x quantity x minus k times q of x plus f of k. Now f of x is going to be quantity x minus k times q of x because f of k is 0. So this part, the zero's out. Now what does this mean? If we show that f of x is just some polynomial times x minus k, that means that x minus k is a factor of f of x. All right, so that's just basically what being a factor means, right? All right, so make sure that this simple but really important theorem is fully understood before you proceed. All right, so these are some of the things we want to keep in mind, that if k is a 0 of a function f of x, then all of the following hold. F of k is 0, just by definition of what the 0 of a function means. K is a solution or root of the equation f of x equals 0, and x minus k is a factor of f of x. Symbolically, we say k is a 0 of f of x if and only if k is a root of f of x equals 0, if and only if x minus k is a factor of f of x. These three statements are basically equivalent. As soon as that you know that you have one of these three facts, you should know that you have all three of them. That's what that means. Now, let's bring this to life with a really simple example. Now, we know that x minus 2 and x minus 3 are factors of this polynomial, f of x equals x squared minus 5x plus 6, given that we can factor x squared minus 5x plus 6 as quantity x minus 2 times quantity x minus 3. Now, note that that means f of 2, which is going to be 2 minus 2, we're just substituting 2 for x, right? 2 minus 2 times 2 minus 3, that's going to be 0 because the 2 minus 2 part becomes 0. And f of 3 as well is going to be 3 minus 2 times 3 minus 3, and the 3 minus 3 part is 0, so the whole thing becomes 0. Finally, note that x equals 2 and x equals 3 are solutions of the equation x squared minus 5x plus 6 equals 0, since you have quantity x minus 2 times quantity x minus 3 equals 0. Now we apply the zero factor property, which says either x minus 2 is 0 or x minus 3 equals 0. So x can be either 2 or 3. So these three concepts go hand in hand, as you can see in this simple example from algebra. All right, so for our first example, we want to determine whether x plus 6 is a factor of x cubed plus 7x squared plus 4x minus 12. And we're going to be using both the remainder theorem and the factor theorem. We know that x plus 6 is going to be a factor of this polynomial if and only if negative 6 is a 0 of that polynomial. And always remember, if it's given to you in the form of a sum, you can easily write it as x minus negative 6, right? Because when we were given the theorem, it was given in the form of x minus k, right? So we need to find out if negative 6, which is our k here, is going to be a 0 of this polynomial. Now that we can quickly do using the remainder theorem. So we're just going to do a synthetic division. So we'll write negative 6 in our box here, and we'll put the coefficients from this polynomial in descending order. And notice there are no missing terms. So 1, 7, 4, and negative 12, right? So remember, we drop the 1 down, and then we multiply negative 6 times 1, which gives us negative 6. We write the result here. We add, we get 1. 1 times negative 6 is going to give us negative 6. Negative 6 plus 4 is negative 2. Negative 6 times negative 2 is 12. So that gives us 0, which we know from the remainder theorem is f of negative 6. All right, so because we showed that f of negative 6 is 0, meaning negative 6 is a 0 of f of x, so therefore x minus negative 6 is going to be a factor of the polynomial. Now, x minus negative 6 is, of course, is x plus 6. Is going to be a factor of the polynomial by the factor theorem. All right, so there's a quick application of the theorem we just learned about. All right, so in our next example, we want to factor this function f of x here completely using the fact that k equals 1 is a 0 of the function. Now that means x minus 1 is going to be one of the factors, right? So we already know this is going to be quantity x minus 1 times some polynomial, right? So, but what we can do now is use the fact that if we divide f of x by x minus 1, the remainder is going to be 0, and it's going to tell us what that q of x is going to be. So that's what we're going to do. Notice descending order and no missing terms. So we go ahead and use 1 in our box over here for our synthetic division, and the coefficients are 2, 3, negative 30, and 25, right? So the 2 drops down, and then we get 1 times 2 is 2, 3 and 2 give us 5, 1 times 5 is 5, negative 30 and 5 is negative 25, and 1 times negative 25 is negative 25, and they of course add up to give us 0. Now this should not be surprising, it's just a nice check for us to make sure that we actually did it correctly, because we were given that k equals 1 is a 0. So that means this, which is equal to f of 1, should be 0. So now this tells me that this is the polynomial that the quotient is, right? So we end up with, this is the 0th power term, this is the first degree term, and this is the second degree term. So x squared plus 5x minus 25, right? So we're going to write f of x as quantity x minus 1 times quantity x squared plus 5x minus 25. Oh, be careful, we dropped a 2. So 2x squared plus 5x minus 25. All right, so now we have f of x equals quantity x minus 1 times 2x squared plus 5x minus 25. But this part is just a quadratic expression, right? We know how to factor these. So we can either find it easily or we may have to do more work, but let's try to see if it just is going to factor, because if it does, we're done. So let's try 2x and x, 25, not that many choices. We'll try 5 and 5, see if it works. Now the inner product is going to be 5x, the outer product is 10x. We want their sum to be positive 5x. That can happen if the 10 is positive and the 5 is negative, right? So if the negative goes there and the positive goes there, okay? So we're going to do a quick check. First times first is first. Last times last is last. And the inner product, which is negative 5x, and the outer product, which is positive 10x, add up to give us the middle term. So that's a correct factorization. And there we have the complete factorization of the polynomial. Okay? Now, no matter what the degree of the polynomial is, once we get to a quadratic part, we're just going to take care of it by factoring or possibly finding the factors using the quadratic formula or completing the square or our method of choice. Okay, for our next one, we're going to factor this completely using the fact that negative 2 is a 0 of multiplicity 2. That means it's a 0 of this function twice. So in other words, x minus negative 2, which is another name for x plus 2, is going to appear in the factorization twice. So we're going to have x plus 2 times x plus 2 times some other polynomial, right? So what we will do is we'll go ahead and start by finding a partial quotient. It won't exactly be this that we're going to find when we divide one time. So, and then we do it again and we'll come up with this quotient, okay? So we know that it goes into it twice. So we'll go ahead and write the negative 2 here. And for our coefficients, we make sure it's in descending order and no missing terms, and that is indeed the case. So we have 1, 3, negative 42, negative 172, negative 168, right? So 1 drops down, so we get negative 2. Negative 2 and 3 add up to give us 1. 1 times negative 2 is negative 2. Those add up to give us negative 44. Negative 44 times negative 2 is 88. Now, we need to subtract 8 from 12 is 4. 8 from 16 is 8. And it's going to be negative. Now we multiply and we get positive 168. And of course, they add up to give us 0 as expected, because we know negative 2 is a 0 of this polynomial twice. All right, so since I know that negative 2 is a 0 of the polynomial twice, I know it should go into it again, right? So this part should be divisible by negative 2 as well, right? This remaining quotient. So we repeat the process again. So we have 1 and then negative 2 plus 1 is negative 1. Negative 1 times negative 2 is 2. Negative 44 plus 2 is negative 42. Negative 42 times negative 2 is 84. And we get 0 as expected. So this is going to be whatever this first polynomial was, right, of negative 2 but notice that it is also f of negative 2. So you can safely say that's f of negative 2 as well. So, but since I was dealing with a different polynomial, I'll refrain from writing that. Okay, here. All right. So, but we have this, right? We have f of x equals x plus 2 times x plus 2 times this quotient, which is the quotient we were referring to at first, right? So now this is of course the constant first, second degree. So x squared minus x minus 42. All right. So basically we have x plus 2 squared times, now we will try to factor the quadratic, right? So x, how about negative 7 and positive 6, right? We're looking to see if the first times first is first, last times last is last. Inner product is negative 7x, outer product is positive 6x. They add up to give us the middle term. It checks out. We've done it correctly. So there is the complete factorization of this fourth degree polynomial. All right. So make sure you can carry on a process like this completely on your own without any help before you proceed. All right, so we've gotten to the point where you should be able to carry these on your own. So try to do it yourself before you rejoin the video. Okay, so we know that we're going to be trying to factor this cubic polynomial by knowing the fact that 2 is a zero of it, right? So we start with going ahead and dividing by x minus 2 to see what quotient remains. So here our factors, we notice that the polynomial is in descending order and it has no missing terms. So 1, negative 8, 37, negative 50. 1 drops down, 2 times 1 is 2, negative 6, 2 times negative 6 is negative 12. Those add up to give us 25. 2 times 25 is 50, and we get 0. Now, we knew that was going to happen. We weren't doing this to verify that. We were just doing this to find this simpler quotient that is going to be a factor of this as well. So far we have f of x equals x minus 2. Remember, when we write this, we're actually dividing this polynomial by x minus 2, right? So, and when we're doing that, remember with synthetic division, whatever this number that comes after x is, you put the opposite here, okay? So that's why we put a 2 there. All right, so times, now, of course, that's going to be constant, first degree, second degree. So x squared minus 6x plus 25. All right, so now at this point, we're going to try to factor this. Now, just by looking at this, I can tell you this is not going to happen because this is not going to factor nicely, not over the set of real numbers. If you remember, we had a check for that. Notice that a is 1, b is negative 6, and c is 25, right? So if you calculate the discriminant, which is b squared minus 4ac, you end up with quantity negative 6 squared minus 4 times 1 times 25, right? So that's going to be 36 minus 100. Now it happens to be negative 64, but I don't even really care about that. I just care about the fact that it's negative, right? That tells me I'm going to have two complex conjugate roots, right? From our previous knowledge. So when that happens, when it's less than 0, you know it's not going to be factorable over the set of real numbers. So previously, in a regular algebra class, intermediate or elementary algebra class, we would just say, okay, this is not factorable. Well, that's no longer going to be the case, because it is factorable. It's just not factorable over the set of real numbers. It's going to be factorable over C, which is the set of complex numbers. So here's what we're going to do. We're going to go ahead and find the factors by solving this equation. Now, we could apply the quadratic, or it looks really nice and simple. So why don't we just practice our completing the square method, okay? So x squared minus 6x equals negative 25. To complete the square, we need to take half of negative 6, which is negative 3, and then square it to get 9. So we need to add 9 on the left side to complete the square, so we'll do the same on the right side. So we get quantity x minus 3 squared equals negative 25 plus 9 from so negative 16. So applying the square root property, we get x minus 3 equals plus or minus square root of negative 16. So we get x is equal to 3 plus or minus, remember, square root of negative 16 is the square root of 16 times the square root of negative 1, so it's 4i. All right, so how does that help me? Because I can now say the factorization is going to be x minus the first 0 of the polynomial times x minus the second 0, which is going to be 3 plus 4i, times x minus the second 0, which is 3 minus 4i. Remember, this is two zeros. The plus case gives you x equals 3 plus 4i. The minus case gives you x equals 3 minus 4i. So we get x minus quantity 3 minus 4i. Now all we're going to do is just clean it up, make it look nicer. So we get x minus 2 times x minus 3 minus 4i times x minus 3 plus 4i. All right, and that is the fully factored form of f of x. So a function that we could not previously factor completely, we can now factor completely using some of the knowledge that we have from the factor theorem and some of the new concepts we're learning, okay? So, of course, you could have just solved this quadratic here using the quadratic formula, and you would have obviously gotten the same answers, okay? I just figured it would be a good opportunity for us to practice completing the square, okay? So make sure you can handle that completely on your own, and we'll proceed. Note that if the problem was only asking you to provide the zeros, then you would have just answered the zeros are 2, 3 plus 4i, and 3 minus 4i, okay? But since it said factor completely, we had to go that extra step and write it out like this, okay? All right, next we're going to look at a very important theorem called the rational zeros theorem that we actually have all the tools we need to be able to prove. So we'll also go ahead and prove it. If P over Q is a rational number in lowest terms that is also a zero of a polynomial function f with integral coefficients, that means the coefficients are integers, then P is a factor of the constant term a0 and Q is a factor of the leading coefficient an. So pay very close attention to the requirement that it's in lowest terms. It's going to play an important role when we prove this theorem. So basically we're saying, look, if P over Q is a factor of this polynomial, then the numerator P is going to be a factor of this constant term, and the denominator Q is going to be a factor of this leading coefficient. Now, this really is going to be relying on this fact that it's in lowest terms, so as you'll see in a minute. Now, given that P over Q, here's the proof. We know that P over Q is a 0 of f. That's given, right? So that means f of P over Q is what? 0, right? So if we just plug in P over Q for x, right, we get an times quantity P over Q to the n plus an minus 1 times quantity P over Q to the n minus 1 plus dot dot dot, which means this keeps going all the way to a1 times x, which is just P over Q, plus a0 equals 0. Now, if I just raise these powers out, I get, in other words, applying the power rule for fractions, we get an times P to the n over Q to the n plus an minus 1 times P to the n minus 1 over Q to the n minus 1 plus dot dot dot. This happens for all the terms in between. And we go to a1 times P over Q plus a0 equals 0. Now, if we multiply both sides by Q to the n, since that's the common denominator of all those denominators, given that that's n is the highest power of Q that is in any denominator, we'll basically clear all the fractions, and we end up with an P to the n plus an minus 1 P to the n minus 1 times Q, because remember, that's Q, we're multiplying by Q to the n, right? So let me handle one of them for you so you see how that works. So keep your attention on this term right here, this second term. So basically you get Q to the n on the top, and you have Q to the n minus 1 on the bottom, right? Of course, alongside an minus 1 P to the n minus 1, right? So notice that, keeping your attention on this object here, this expression, we get Q to the n minus quantity n minus 1, right, by the quotient rule. It's always, when you divide two powers with the same base, you keep the base, you subtract the exponents, and you end up with Q. Now that's n minus n plus 1, right? So what is it? That's Q, because n minus 1 is 0 plus 1 is 1, Q to the 1 is Q. So that's why suddenly this became just Q, right? All right. Now here we get a1 P Q to the n minus 1, because it's Q to the n and then over Q, right? Using the same argument we just made over here. So it's the numerator on the Q exponent on the top is going to be n, and the exponent on the bottom is 1. That's where you get this. And then plus a0 Q to the n, okay, is equal to 0. Remember, we're just multiplying both sides of this equation by Q to the n. All right, and now what we're going to do is we're going to keep all these guys here on the left side, and we're going to move this one term to the right side. So that's why it becomes negative a0 Q to the n. Now, all of these have a power of p in them, right? So we can factor out a p. And that leaves us an p to the n minus 1, because remember, I'm factoring out a p, so you're going to end up dividing that by p, so you get p to the n over p to the 1, which is p to the n minus 1, plus an minus 1. Now, same thing here, we're dividing by p, so that's going to be p to the n minus 1 minus 1. That's how you get n minus 2. And then this process continues until we get to this term, so we get a1 q to the n minus 1, right? The p's cancel out in the last term, right? Is equal to negative a0 q to the n. So this means that p is obviously a factor of this expression on the right. Why? Because it's the expression on the right is p times some polynomial, right? Now, p over q is in lowest terms, right? That means the greatest common divisor between p and q is 1. So p can't be a factor of what? Q to the n. Therefore, p must be a factor of what? The only thing that's left, which would be a0, right? So that's how we show that the numerator of the quotient that's going to be a 0 of this function must be a factor of the constant term in the polynomial. Okay? So this algebra looks advanced, but if you just pay attention to it, you can do it. The thing to do is to run through this for yourself. That's how you get better in mathematics, okay? Not by running away, but by what seems to be a little bit different or difficult, but by running toward it. I mean, you should be able to write this down and now walk through this completely on your own if you really want to make yourself better in mathematics and reasoning in general, okay? So now, in order to show the other part, that q is a factor of the leading coefficient an, here's what we're going to do. We've done all the work that has gotten us here, right? Well, this is where we're going to pick up. Now, we already have established this, right? So we can use it again. So we're going to start with this line right here. Now, this time, instead of moving the a0q to the n to the other side, we're going to keep it on this side. And instead, we're going to move that first term an p to the n to the other side. Of course, on that side, it becomes negative because basically we're subtracting it from both sides, right? Now, on the remaining terms on the left side, notice they all have a factor of q, right? So we can factor out the q, and that's going to leave us an minus 1 p to the n minus 1. Here in the first term, the q's cancel out, and then the process will continue until you get here. That's going to be a1 p q to the n minus 2, because what's q to the n minus 1 divided by q? Well, it's going to be q to the n minus 1 minus 1, right, which is n minus 2. Same thing with this, all right? Now, that tells you that q is going to be a factor of what? This expression on the right, right? And again, given that p over q is in lowest term, the greatest common divisor of p and q is going to be 1. So q is not a factor of the p to the n part, right? The only thing it can be a factor of is what? an. So now we've established that p is a factor of a0 and q is a factor of an. And this filled square here, of course, means QED. That means our proof is over, and that which was to be shown has been shown, which is what QED stands for, quod erat demonstrandum. It's Latin for exactly that. It means that which was to be shown. All right. So now we keep that important fact in mind. That narrows down the number of possible zeros that we could be looking for when trying to factor a higher degree polynomial, right? We know that if there's going to be a rational root or a rational zero of the polynomial, or root of the polynomial equals 0, that equation, then we know that the numerator is going to have to be a factor of this constant term, and the denominator is going to have to be a factor of this leading coefficient. All right, again, I would definitely try to run through these for yourself if you really want to improve yourself in mathematics. Just being able to crank out homework problems, that's not really how you make progress in math. But getting into the subtleties of the subject, that's where the magic happens. All right, let's go ahead and try to find all the rational zeros of this fourth degree or quartic polynomial, 6x to the 4 plus 7x cubed minus 12x squared minus 3x plus 2. And once we find the factors, we're going to go ahead and once we find the zeros, we're going to go ahead and factor it into a number of linear factors. All right, notice here that the constant term here, which we refer to as an, right, is 2, and the lead coefficient, which referred to as a0, is 6. So suppose P over Q is a rational zero of F, right? So what are the possible values for P? So possible p-values. Remember that p, the numerator of the fraction that's going to be as rational zero of this polynomial, is going to have to be a factor of the constant term. So the possible p-values, what are factors of 2? That's easy, right? Either positive or negative 1, or positive or negative 2, right? All right, so what are the possible q values? Well, they're going to have to be factors of 6, right? So what are all the possible factors of 6? We have positive or negative 1, positive or negative 2, positive or negative 3, but don't forget also positive or negative 6, right? So now we want to see what are the possible P over Q values, right? So just be systematic about this. Just, you have two choices here. So first take care of the quotient of the first number 1 in both positive and negative form by each of these, right? So positive or negative 1 divided by positive or negative 1 gives you positive or negative 1. Positive or negative 1 divided by positive or negative 2 will give us positive or negative 1/2, right? Positive or negative 1 divided by positive or negative 3 gives us positive or negative 1/3. And positive or negative 1 divided by positive or negative 6 will give us positive or negative 1/6, right? Now we move to 2. So positive or negative 2 divided by positive or negative 1 will give us positive or negative 2. Positive or negative 2 divided by positive or negative 2 will give us positive or negative 1, which is already covered. We don't need to write it again. Positive or negative 2 divided by positive or negative 3 will give us positive or negative 2/3. And positive or negative 2 divided by positive or negative 6 will give us positive or negative 1/3, 2/6 or 1/3, which we've already covered. We don't need to write it again. So there they are. Here you have all the possible values for the rational zeros of this function in reduced form. Remember, it's just this theorem just tells you what they could be. It doesn't tell you which ones they could be, correct? So now it's time to grind, right? Now we're just going to have to try till we hit some numbers. Now, obviously, positive or negative 1 and positive or negative 2 are the nice, easy ones to work with. So why don't we just start trying those systematically, right? Hopefully we'll hit enough zeros in that bunch so we don't have to deal with the fractions. But if we have to, we will. So let's go ahead and just start with 1. Let's see if 1 is a 0 of this polynomial. So that means we're going to go ahead and do a synthetic division by dividing this polynomial by x minus 1. So we're testing x equals 1. Now, this polynomial is in descending order and there are no missing terms. If there were, it would be no big deal, right? We would just put a filler. Like if the negative 3x was happened to be missing, we would just put plus 0x and we would use 0 for the coefficient. So not a big deal. So 6, 7, negative 12, negative 3, and 2. We drop the 6 down. 1 times 6 is 6. Now 6 and 7 is 13. 13 times 1 is 13. Minus 12 is 1. 1 times 1 is 1. And negative 3 is negative 2. 1 times negative 2 is negative 2. And that gives us 0. So we got really lucky. Our very first attempt worked out. All right, so now we're going to go ahead and try maybe negative 1, okay? So now remember, you don't have to go back to the original function to try negative 1. You can just try it with what this reduced quotient that's left over, right? So we'll go ahead and see if negative 1 works with that one. That means we're trying to see if x plus 1 is a factor, right? So we drop down the 6. Negative 1 times 6 is negative 6, and 13 gives us 7 times negative 1 is negative 7, and that gives us negative 6. Negative 1 times negative 6 is 6, and this one did not work, right? So negative 1 is not a 0 of the polynomial. That's no problem. We'll go ahead and move on to our next one, which is 2, right? So I'm going to go ahead and erase what I did, otherwise we'll run out of space. So negative 1 didn't work, so we'll go ahead and now we'll try 2. Remember, we're going to try the nice numbers first. Now 2 times 6 is 12. 12 and 13 is 25. 25 times 2 is 50. 50 and 1 is 51. Already I can tell you it's not looking promising, right? So 2 times 51, that's 102. And of course, do I need to even calculate this? No, I just know it's not 0, right? So I stop. So this one didn't work either. Well, it happens to be 100, right? But it doesn't matter because that has to be 0 for it to be a 0 of the polynomial. So 2 didn't work. Let's go ahead and erase, and we'll patiently move on to negative 2. Let's try negative 2. So bring 6 down, so we get negative 12. 12 and negative 13. I mean, negative 12 and 13 is 1. It's looking good, right? When the numbers stay small like this, it's promising. So negative 2 and 1 is negative 1. Negative 1 times negative 2 is 2, and we have a hit. Okay. So what have we accomplished so far? We have shown that f of x is x minus the first 0, 1, times x minus the second 0, so x minus negative 2. What does x minus negative 2 become? It becomes x plus 2, times this leftover quotient, right? So constant, first degree, second degree, 6x squared plus x minus 1. Now, once the only non-factored factor in the factorization, that's a lot of factors there, right, is a quadratic one, you don't really need to do the, use the remainder theorem and all that anymore, because it's a quadratic. You know how to factor it one way or another, right? Either it's going to play nice and just be factorable over the set of real numbers, hopefully over the set of integers even, right? Or you go ahead and go to the quadratic formula or completing the square. With this one, given that the lead coefficient is not 1, I wouldn't choose completing the square. I would use the quadratic formula. But let's see if it factors or not. It might be nicer than it looks. All right, so quantity x minus 1 times quantity x plus 2. So we're just going to do the trial and error FOIL method. So why don't we try 3x and 2x. Yeah, this looks very promising. We want positive x, so we'll put a plus 1 here and a minus 1 here. First times first is first, last times last is last, inner is negative 2x, outer is positive 3x. They add up to positive x. So we have completed the factorization, and there is. All right, if you were to list the zeros of the function, what were they? 1, negative 2. To get the other two, you're going to have to just put these two factors, set those equal to 0. So 3x minus 1 equals 0 gives you 3x equals 1, or x equals 1/3. And 2x plus 1 equals 0, so 2x equals negative 1, or x equals negative 1/2. So there we have all the zeros of this function. 1, negative 2, 1/3, and negative 1/2. If you want to present it as a solution set, well, not really, because we're not talking about the equation f of x equals 0. We're just talking about the polynomial. So just leave it like that. Those are the zeros, okay? All right. If they had said solve f of x equals 0, then you would present a solution set, and you would represent the same numbers in a solution set format, like so. Okay, so there is a nice problem with an application of what we have just learned. What I really want you to focus on is how closely connected these concepts of zero of a polynomial, roots of the polynomial equals 0, and factors of the polynomial are together, how closely connected they are, these concepts together. And you'll be in great shape once you understand that. And of course, graphically speaking, we also know that we're also looking at the x-coordinate of the x-intercepts of the graph of the polynomial as well when we see those as zeros. All right, so let's go ahead and move on. All right, so here's a general note about what we just experienced, and that is the fact that once the factorization progresses to a point where the highest degree factor left in a quadratic is a quadratic one, you can abandon the remainder theorem approach and try to factor the quadratic factor. If that is not possible, you can just use the quadratic formula to find the remaining linear factors of the polynomial. Well, first you'll find the zeros, right? Then you'll just put x minus each of those zeros as one of the factors remaining. A couple of other important notes. The rational zeros theorem, as I already mentioned, only tells you the possible rational zeros of a polynomial. It does not tell us what those zeros are, right? The rational zeros theorem only applies to polynomials with integral coefficients. Remember, that was there when we stated the theorem, correct? Which means integer coefficients, right? However, there's a workaround if the coefficients are rational, okay? As long as the coefficients can be either written as a quotient of two integers with the denominator not being 0, or as a terminating or repeating decimal, then we can go ahead and just clear the fractions or the expressions or the decimals in the expression that defines the function, and then apply the theorem. For example, the zeros of this function f of x equals 1/2 x cubed plus 1/3 x squared plus 1/4 x plus 1/5 will also be zeros of this cleared one, where we notice that the least common denominator is 60. So if we multiply both sides by 60, we end up with g of x equals 30x cubed plus 20x squared plus 15x plus 12, right? Just multiplying these guys, not both sides, just this function by 60, right? Now, the reason we can do that is because basically when you set this function equal to 0 and this other one equal to 0 and solve, they will have the same roots because they're equivalent equations, in the sense that one equation will be a constant factor of the other equation. We know that whenever one equation is a constant factor of another one, they're going to have the same roots. For example, if you look at x minus 2 equals 0 and look at 2x minus 4 equals 0, then this equation has solution x equals 2. And this equation is nothing but that equation times 2 on both sides, right? So multiply both sides of this equation by 2, you'll end up with this equation. But notice, if you solve it, they'll end up giving you the same solution. That's why this works, okay? All right. So those are important notes to understand. Make sure you absorb them, and we'll proceed. All right, next we're going to represent the fundamental theorem of algebra, which says every function defined by a polynomial of degree 1 or higher has at least one complex 0. Now, we will find out in a minute that, for example, if you have an nth degree polynomials, it will have n zeros. However, they don't necessarily have to be what? Different ones. They may be repeated zeros. Now, if you just think of what we just learned, it follows directly from that if the degree of a function f of x is greater than or equal to 1, then there's going to be some constant, some complex constant c1, such that f of c1 is 0, right? Now, by the factor theorem, that means that x minus c1 is going to be a factor of f of x. So we're going to have quantity x minus c1 times g1 of x for some polynomial g1 of x, right? Now bring your attention to this g1 of x. Now, what happens? What if that happens to have a degree greater than or equal to 1 as well? Then the fundamental theorem and the factor theorem again mandate that there should be some other constant c2, such that g1 of c2 is 0 and g1 of x becomes quantity x minus c2 times that g2 of x, right? So now we should be able to write f of x as quantity x minus c1 times g1 of x, which is now this. So times quantity x minus c2 times g2 of x. Now, if we assume that f of x has degree n, and we repeat this process n times, we get f of x is equal to a times, I don't know why I wrote that twice, don't ask, but that should be only once. Let me clean it up. Okay, I feel better now. So we get f of x equals a times quantity x minus c1 times quantity x minus c2 all the way to quantity x minus cn, where a is the lead coefficient of f of x. So this basically tells us that f of x would have n zeros. And this analysis suggests the next theorem we want to look at. the number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct zeros, right? That is going to become very clear once we do a few examples. All right, so here we want to find a polynomial f of x of degree 3 with real coefficients and zeros -3, -1, and 4, for which f of -2 equals -24. Well, I think you'll agree that it's very easy to set up a polynomial which has a certain number of a certain group of zeros, right? We can just go f of x equals quantity x minus the first zero, so x minus -3, which becomes x plus 3. Let me leave some space here. I'm going to need it. So x plus 3, and then x minus the second zero, so x minus -1, which becomes x plus 1, times x minus the third zero, which becomes x minus 4. Notice if I look at just that polynomial, right, it's going to have these zeros, right? Imagine putting this equal to 0. Each one of these will end up being a solution of that equation, and of course each of them will also be called a zero of the polynomial. But this is not the only polynomial that's going to have these zeros. I can take this polynomial and multiply it by any constant that I want, and that polynomial is still going to have the same the same zeros. Multiplying by this constant is not going to matter, but we want this constant because now we can custom design this particular polynomial so that f of -2 equals -24. So f of -2, which is going to be a times, remember we're going to plug in -2 for x, like so, right? And remember, this f of -2 we're going to replace with -24. So we get, now here we have what? Here we have 1. Here we have -1. So we get a times 1 times -1 times -6, right? Now 1 times -1 times -6 is just 6. So we get -24 equals 6a. So that's going to make a -4. We just divide both sides by 6, right? All right, so we have the a. So now we know our function f of x is going to be -4 times x plus 3 times x plus 1 times x minus 4. So now it's just a matter of multiplying it out. So we get -4 times x plus 3. Let me go ahead and multiply those two out. So I get x squared. Here we're just multiplying x by both of those, so minus 4x. And we'll go ahead and multiply the 1x, and minus 4, so plus x minus 4. So we get -4 times x plus 3 times x squared minus 3x, right, minus 4. So now we need to multiply those two polynomials. I like to do those in a table. So I put x squared minus 3x minus 4 here, and put x plus 3 here. And now we get this. So x times x squared, that's just x cubed. X times -3x will give us -3x squared. X times -4, we multiply it out just like a times table, right? +3 times x squared gives me +3x squared. positive 3 times negative 3x is negative 9x, and positive 3 times negative 4 is negative 12, right? So I notice that basically we combine everything inside the box here, and that's going to be our result, right? So I notice these cancel out. So that's going to simplify things quite a bit. So now we get equals negative 4 times x cubed minus 13x. We combine the like items, right? Those two are like terms, right? And then minus 12. So now finally we go ahead and multiply the negative 4 into that. So negative 4x cubed plus 40 and 12 is 52x, and then plus 48. So there is the custom designed polynomial that we were asked to find. So it is a third degree polynomial, a cubic polynomial, and there is the exact polynomial. Okay, so a nice little practice. Make sure you can handle it before you proceed. All right, so here's one you should be able to handle. You should definitely pause and try it on your own before coming back. All right, so we know that we can set up a polynomial with these given zeros, negative 7, 2, and 0 very quickly. We can just say f of x equals that constant a, remember, times x minus the first 0, negative 7. So x minus negative 7 turns into x plus 7, times x minus the second 0, which is 2, times x minus the second 0, which is just 0, so x minus 0. And we also know that f of negative 5 equals negative 1. We're going to be using that in a minute. So let's simplify this a little bit. So that's f of x equals, now that's just x, right? So we can just say ax times x plus 7 times x minus 2. Now we want f of negative 5. So that's going to be a times negative 5, x is negative 5, and x plus 7 becomes negative 5 plus 7, and x minus 2 becomes negative 5 minus 2. So with f of negative 5, we want to replace it with negative 1. On this side, we have a times negative 5 times negative 5 plus 7 is 2, and negative 5 minus 2 is negative 7. So we have negative 1 equals, now that's negative, so negative times negative is positive, so we're going to have 70, right? So 70a. So a is going to be negative 1 over 70. So we have our function f of x. It's going to be, I'm going to use this simplified form. So negative 1 over 70x times x plus 7 times x minus 2. So f of x equals negative 1 over 70x times, let's go ahead and multiply this out. We'll do it more quickly this time. So it's going to be x squared. And then we know the middle term is going to be 7x minus 2x, so 5x. And then minus 14, right? So now we're going to distribute the negative 1 over 70x. So we get negative 1 over 70 x cubed minus 5 over 70x plus x squared, that is, plus 14 over 70x. So now we noticed we can do some simplifying. We know 5 goes into 70 14 times, which means 14 goes into 75 times. So now our final simplified polynomial is going to be f of x is equal to negative 1 over 70 x cubed minus 1 over 14 x squared plus 1/5 x. And that's all there is to it. Okay, so make sure that you have this down, and then we'll proceed. All right, so try this one, see what you come up with. Find the polynomial function f of x of degree 3 with real coefficients that satisfies the following conditions. 0 is a 0 of f of x, 3 is a 0 of multiplicity 2, and f of 4 equals 24, sorry. All right, so we know we can set this up as such. F of x is going to be a times x minus 0 times x minus 3, and then another x minus 3, right? Because it's a 0 of multiplicity 2. So let's clean it up a little bit. So we get f of x equals ax times x minus 3 squared. Quantity x minus 3 squared. Okay, so now we can take the last piece of information given and apply it. F of 4 equals 24. So f of 4, which is going to be a times 4 times 4 minus 3 squared, and we're going to replace the f of 4 with 24. So we get 24 equals a times 4. Now 4 minus 3 is 1. When you square that, you get 1. So we get 24 equals 4a. So a is going to be 6. So let's take this one and substitute a. So we get f of x equals 6x times x, quantity x minus 3 squared. Notice this is, an adequate answer in itself, but we usually like to, expand it out and multiply it out. So we get f of x equals 6x times, we're going to go ahead and square x minus 3. Remember the formula, quantity f minus l squared equals f squared minus 2fl plus l squared, right? So we get x squared minus 6x plus 9. Now we just need to multiply the 6x into that trinomial. So we get f of x equals 6x cubed minus 36x squared plus 54x. And that's all we have to do there. There is the polynomial requested. Okay, not too bad, right? All right, let's do one more of these before we move on to complex conjugates. Okay, so find the polynomial f of x of lowest degree with only real coefficients and having the zeros 5 plus radical 2, 5 minus radical 2, and 4. So everything about it is going to be the same. It's just that arithmetic might get a little bit more involved. So we have f of x equals a times x minus the first 0. Let me put the 4 first. Doesn't matter the order, right? And then times x minus the second 0, f5 plus radical 2. Make sure you parenthesize it because the negative needs to be distributed. And then times x minus quantity 5 minus radical 2. Okay, so we get a times x minus 4 times, I'm going to go ahead and get rid of the brackets, so I'm going to multiply the negative out, x minus 5 minus radical 2 and times x minus 5 plus radical 2. Now notice that I'm not given any other restrictions such as a particular value for f at a given point, and so I can just assume a is 1, right? So if it's 1, I can just pretty much erase it, right? There you go. So I'm just going to let a be 1. So I get f of x is equal to this expression here. Now you can multiply this out rather quickly if you realize something nice, which is you can think of the product of these two expressions here like this. You can say x, you can group x minus 5 together, say x minus 5 minus radical 2 times x minus 5 plus radical 2, right? Now this looks like what? F minus L times F plus L. Remember what that is? That's a difference of squares formula. So that means I can now say f of x equals x minus 4 times, remember this is going to be, think of x minus 5 as f and the square root of 2 as L, right? So it's going to be quantity x minus 5 squared minus square root of 2 squared, and that's just 2, right? So it's x minus 5 squared minus 2. So times, let me use bracket, quantity x minus 5 squared minus 2. So now we'll go ahead and figure out x minus 5 squared, and we just saw the formula, so it's going to be first one squared minus 2 times first times second, so minus 10x, plus the second squared, so 25, and don't forget there's a minus 2. So we end up with f of x equals quantity x minus 4 times x squared minus 10x plus 23. As always, remember you should be giving these your own absolute best shot before coming back to look at the rest of the video, if you want to really get maximal benefit from the lectures, right? All right, so now we're just going to multiply those two polynomials. You know me, I like to do those using a table. So I have x minus 4, x squared minus 10x plus 23, and we're just going to multiply it out like a times table. So we get x cubed minus 10x squared plus 23x, and then in the second row we'll have negative 4x squared plus 40x, and then 4 times 20 is 80, 4 times 3 is 12, so 92, negative 92. Okay? So we can group these two x squared terms together. We can also group those two x terms together, right? Because they're like terms. So we end up with x cubed minus 14x squared plus 63x minus 92. And there we have our custom designed function. All right. So make sure that you can process that on your own, and we'll move on to another topic. All right, next we want to talk about complex conjugates. The two complex numbers a plus bi and a minus bi are called complex conjugates of one another. Notice they're pretty much identical, except in here these two are being added and here we have a subtraction, right? So we use a bar above a complex number to designate its conjugate. So the conjugate of a plus bi, that's how you read that. The conjugate of a plus bi is equal to a minus bi, and the conjugate of a minus bi is a plus bi. Clearly, conjugateness is a mutual relationship. All right, first we want to learn about a few properties of conjugates which are important and which we're going to use in a proof that's coming up. So first thing is that the conjugate of a sum is the sum of the conjugates. That's how you read that. You say the conjugate of a sum is the sum of the conjugates, okay? So here's how we can prove it. Let Z1 be a plus bi, and let Z2 be c plus di. Remember, after all, they're just two complex numbers. Then let's take a look at what the conjugate of the sum looks like. So that's going to be the conjugate of a plus bi plus c plus di, right? Now, if I team up the real parts together and the imaginary parts together, I end up with this, right? Here I can factor an I out, so I get quantity a plus c plus quantity b plus di, right? Now, but that itself is just going to be a complex number, right? Because the sum of those two is just some real number. The sum of those two is just some real number. So what is the conjugate of a real number? Just change the plus to a minus. So I can drop the conjugate symbol now and just write what the conjugate is. So it's going to be quantity a plus c minus quantity b plus di, right? So that basically means a plus c minus bi minus di. Now group a and b together, so you get a minus bi, and we'll group c and di together, so you get plus c minus di. But remember, what's a minus bi? That's just the conjugate of z1, right? What's the conjugate of z1? A minus bi. And what is c minus di? Notice that's just the conjugate of z2. So we just showed that the conjugate of the sum is the sum of the conjugates. So we're done with that QED. Now, you can also show that the conjugate of a product is the product of the two conjugates as well. So for this, we'll take a different approach. We'll show what the conjugate of the product is, right? And then we'll also show what the product of the conjugates is, and then end up showing that they're the same, okay? So we'll start with the conjugate of the product. So notice that here I get AC plus ADI plus BCI plus BDI squared, right? Now, remember what I squared is. That's -1. So this becomes negative BD. So I get AC minus BD plus quantity AD plus BC, and I'm going to factor out the I, right? So now again, I just have a complex number. That's some real number. That's some real number. So what's the conjugate? It's going to be the same thing, but change the plus to a minus, right? Now take a look at the product of the two conjugates. That's going to be a minus bi. That's the conjugate of z1 times c minus di, which is the conjugate of z2, right? So now we multiply it out, so we get AC minus ADI minus BCI, and then plus BDI squared, right? Once again, this is going to become negative BD, right? Because I squared is -1. So we get AC minus ADI minus BCI minus BD. And now I'm going to put these two together, AC minus BD, and I'm going to factor out a negative and an I, and I'm going to be left with AD plus BC. But look what we have. Exactly the same thing that we found when we found the product, the conjugate of the product. Therefore, the conjugate of the product is the same as the product of the conjugates, and we've proven it. All right, the last thing that we want to know is that the conjugate of a power is the power of the conjugate. Okay, that's how you would say that. Now, this proof actually requires something called mathematical induction, which we have not studied yet. So here, you're just going to take my word for it, okay? It is true. All right, at some point, if you continue with math, you'll learn about mathematical induction, and then it'll be a pretty straightforward proof using that technique. But we will use it, okay? So do learn it, okay? Let's move on. Now we want to look at what's called the conjugate zeros theorem. Now, if f of x defines a polynomial function having real coefficients, and if complex number z equals a plus bi is a zero of f of x, then z bar, or z, the conjugate of z, is going to be a zero of the function as well. So they go together. Anytime one complex number of the form a plus bi is a zero of a function, then its conjugate is also going to be a zero of it. Here's the proof, which is going to require the properties we learned in the previous screen. Okay, let f of x equal an x to the n plus an minus 1 x to the n minus 1, etc., all the way to a0 be a polynomial function with real coefficients. Now let z equal a plus bi be a zero of f of x. Then notice that because z is a zero of f of x, if we just plug in z wherever we see x in the definition of the function, that's going to end up making the function zero because it's a zero of it, right? So an z to the n plus an minus 1 z to the n minus 1 all the way to a0, that's going to be 0. Now, if we take the conjugate of both sides, watch what happens. On this side, the conjugate of this sum, as we've learned, is going to be the sum of the conjugates, right? Now, what's the conjugate of 0? That's just 0 itself, right? Because you can think of 0 as 0 plus 0i, right? So the conjugate is going to be 0 minus 0i, which is still what? 0, okay? So now, notice that I can now take the an out because that's just a constant, right? That's being multiplied by this complex power. So I get an times the conjugate of z to the n times an minus 1 times the conjugate of z to the n minus 1, etc., all the way to the conjugate of a0, which is itself. Remember, if you have a constant like 2, right? That's like 2 plus 0i, right? So what is the conjugate of 2 going to be? Well, it's going to be the conjugate of 2 plus 0i. So the conjugate of 2 is going to be 2 minus 0i. But what is that? That's just 2, right? So that's true for any constant that you have. So you're going to be able to do that for. So the conjugate of a constant is itself, right? So now remember the fact that the conjugate of a power is the power of the conjugate, right? So I can move the conjugate to the z level, right? So I get an times the conjugate of z to the n plus an minus 1 times the conjugate of z to the n minus 1 all the way to a0 is 0. But what does that mean? That means if you plug in z conjugate for x, it ends up making the function 0, so therefore f of z bar is also equal to 0. This makes z bar, which is a minus bi, also a 0 of the function. So there's the proof of the fact that if a given complex number a plus bi is a 0 of a function, then its complex conjugate a minus bi is also going to be a 0 of that function. All right, here we want to find a polynomial f of x of least degree with real coefficients that satisfies the following condition. 3 minus 7i and 3 plus 7i are zeros of the function. Okay, so we can assume a is 1 here again because we're not given any initial condition. So we can just say f of x is equal to quantity x minus quantity 3 minus 7i times quantity x minus quantity 3 plus 7i. So if we just simplify a little bit, we get x minus 3 minus 7i times x, actually that becomes plus, sorry, the first one. So x minus 3 plus 7i times x minus 3 minus 7i, right? Now, if you remember the trick I showed you a little bit earlier, think of the x minus 3 as f, and think of the 7i as L. So we have what? We have f plus L times f minus L, which is what? F squared minus L squared. So we're going to get quantity x minus 3 squared minus quantity 7i squared. So that's going to be x squared minus 6x plus 9 minus 49i squared. Now remember what I squared is? That's negative 1. So this negative and that negative are going to multiply to give us plus 49. So we get equals x squared minus 6x plus 9 plus 49. So plus what? 58. There's your polynomial of least degree, which means it's going to be a second degree polynomial with these numbers, complex numbers, being its zeros. All right, so nice little problem. Make sure you can handle it. Go ahead and give this one a try. Find a polynomial function f of x of least degree with real coefficients that satisfies these conditions. 3 is a 0 of multiplicity 2 of f of x, and 3i is a 0 of f of x. Now, they don't give us one of these like f of 2 equals 7, etc. That's called the initial condition, right? So we don't have any initial condition, so we're going to just let a be 1. So we can just say f of x equals quantity. Now, 3 is a 0 of multiplicity 2, so x minus 3 times x minus 3, right? And 3i is a 0 of f of x, right? So x minus 3i, what does that tell you? That tells you, this implies, they don't tell you this, but this implies negative 3i is also going to be what? A 0 of f. Why? Because of the complex conjugates theorem. Anytime a complex number of the form a plus bi is a 0 of a polynomial, so is its conjugate. Now you may go, where's the a plus bi here? Well, 3i you can think of as 0 minus 3i. So the conjugate of 3i is going to be that, which is going to be what? 0 plus 3i, which is just what? 3i. Which is negative 3i, okay? 3i, okay, 3i, sorry, I had a mistake here, 0 plus 3i, so the conjugate is going to be 0 minus 3i. There we go. Now, the 3i you can think of as 0 plus 3i, so the conjugate of 3i is the conjugate of 0 plus 3i, which is 0 minus 3i, which is just what? Negative 3i. All right, so I need to bring in what? X minus negative 3i as well, which turns into what? X plus 3i. Remember, x minus negative 3i, that becomes x plus 3i. Okay, so there it is. We just need to multiply it out, right? So we have, for the first two, I know that's just x squared minus 6x plus 9, right? Now these two, that's a product of two conjugate binomials, right? We know that is going to be f squared minus l squared, right? So think of x as f, think of 3i as l. So it's going to be x squared minus quantity 3i squared, right? So we get x squared minus 6x plus 9 times x squared minus 9i squared. Now, remember what I squared is, right? It's -1. So we're going to get x squared minus 6x plus 9 times x squared plus 9, right? So go ahead and multiply them out, your favorite method, you know mine. All right, so we get x to the 4 minus 6x cubed plus 9x squared plus another 9x squared minus 54x plus 81. Be careful because of that missing power here. You're jumping from x squared to 9. Your grouping isn't going to be nice like it used to be, right? Like in a diagonal manner. So notice that I can go ahead and group (9x squared) with 9x squared, right? And that's the only grouping that's possible. There are no other like terms. So finally we say f of x equals x to the 4. We'll put it in descending order, minus 6x cubed. Now the two 9x squares are going to give me 18x squared minus 54x, and then finally plus 81. Okay? So there's the final answer there for that function. All right, so make sure you can do this and we'll move on. All right, here we're going to factor f of x completely using the fact that 4 minus I is a 0 of f of x. And we're going to first find the zeros, of course. All right, so since 4 minus I is a 0 of f of x, that means I can divide this polynomial by x minus that, and the remainder should be 0, right, by the remainder theorem. So I'm going to go ahead and put 4 minus I in the little box, and we're going to go ahead and perform synthetic division. I notice these are in descending order. There are no missing terms, so I have 1, -12, 49, and -68. The 1 drops down, so I get 1 times 4 minus I, that's 4 minus I. Now we combine these two, so the real parts can combine, so we get -8 minus I. So we're going to multiply those two. Let's take care of that on the side here. 4 minus I times -8 minus I, right? So that's going to be what? -32 minus 4I plus 8I plus I squared, which is -1. So -33 plus 4I. Okay? So that goes here. So when I combine these two, right, what do we get? We get 16 plus 4I. So now we're going to multiply 4 minus I by 16 plus 4I. So we get 64 plus 16I, right? I just distributed the 4. Now I'm going to distribute the negative I. So minus 16i and then plus 4i squared, right? Which I know is negative 1. So I get 60 in the two 16i and negative 16i cancel out. So I get 64 minus 4. Okay, just notice this should be a minus here, not plus 4i squared. Did you catch that? That's a minus 4i squared, right? Because negative I times positive 4i, that's minus 4i squared. So the negative and negative will make a positive. We get 64 plus 4, which is what? 68. So now we can see that it's 0 as expected. Why did we expect it? Because they told us 4 minus I is a 0 of this function, right? So we expect this to happen. We're not surprised by it. All right, so remember, this is f of 4 minus I by the remainder theorem, okay? So we know that if 4 minus I is a 0 of this polynomial, right? 4 plus I should be a 0 as well. So it should go into this remaining polynomial, right? Which is basically x squared plus this number times x plus this number, right? So we'll go ahead and just do a synthetic division with 4 plus I. And we know that should end up being 0. If it doesn't, that means we did something wrong. So 1 here, 1 times 4 plus I is 4 plus I. And combining those will give us negative 4. Because the negative I and the I cancel out. Negative 4 times 4 plus I is going to be negative 16 minus 4i. So we got 0 as expected. So now we're ready to write the factorization of this polynomial. So f of x is going to be x, quantity x minus the first 0, which is 4 minus I. Let me use a bracket at first. Times quantity x minus quantity 4 plus I, which is the second 0, times this polynomial that's left. That's just a constant term, and that's an x term. So x minus 4. So let's continue up here. And just write the simplified form. So it's going to be quantity x minus 4 plus I times, I'm just multiplying the negatives in, x minus 4 minus I and x minus 4, just like that, okay? So there is the completely factored form of this polynomial. These are, of course, all linear expressions, so they're called linear factors of this cubic polynomial, okay? All right, so make sure you have that down. And if they just want the zeros, what would you say? The zeros are 4 minus I, 4 plus I, and whatever you get when you set this equal to 0, right? And x minus 4 equals 0 gives you x equals 4. All right, so there are the zeros of the polynomial. Okay, so let's go ahead and move on. All right, I know this is going to be one of our longer videos, so I apologize, but such is life. Sometimes the concepts just need a little bit more explanation. Otherwise, I could just leave you to figure a lot more on your own, but I know sometimes it's nice to have something to refer to when things get a little bit tougher. So hang in there. This is the last concept and we'll be done after this, okay? So Descartes' rule of signs. This French genius mathematician Descartes did a lot, and here's one of the things that he did. So let f of x define a polynomial function with real coefficients and a non-zero constant term, with terms in descending powers of x, okay? So like the standard kind of polynomial we've been seeing. Now, what Descartes' rule of signs tells you is something about the signs of the zeros of a function. Now, the number of positive real zeros of f of x either equal the number of variations in sign occurring in the coefficients of f of x, or is less than that number of variations by a positive even integer, okay? So the same goes with the number of negative real zeros, but except what you have to do is find the number of variations in sign for f of negative x rather than f of x. And in that case, the number of negative real zeros, real, remember the important word real, is going to be either the number of variations or less in the signs of f of negative x, or less than that number by a positive even integer, okay? So let's go ahead and see it in practice. So determine the different possibilities for the number of positive, negative, and non-real complex zeros of the following function. Okay, so here we have f of x. So before we do anything else, what I would like to do is go ahead and figure out f of negative x as well. And then we'll answer the questions, okay? So f of negative x, that's just going to be 9 times quantity negative x cubed minus 10 times quantity negative x squared plus 9 times quantity negative x plus 1, right? So it's going to be, that's going to be negative x cubed, so negative 9x cubed. This is going to become positive x squared, so just minus 10x squared minus 9x plus 1, right? Okay, so now let's look at the number of variations of sign in the coefficients of the original function, right? So notice we start positive, right? From positive to negative, that's 1 change, right? From negative to positive, that's 2. And positive to positive, there's no change. So the total number of sign changes, right, was 2. Now, let's go ahead and do the same thing. The number of sign changes in, so the first one was in f of x. Now we're going to do it for f of negative x. Now we already have f of negative x, so it was 2 for f of x. Now, for f of negative x, from negative to negative, no change. Negative to negative, no change. Negative to positive, 1 change. All right, so now we can kind of set up a table to answer quickly the questions asked. So in our table, we'll go ahead and write the number of positive zeros, possible number of positive zeros, negative zeros, and non-real complex ones, right? Now, we know that we're looking at a total of 3 zeros because it's a third degree polynomial, right? So now we know that the number of sign changes in f of x was 2, right? So the number of positive zeros is either going to be 2, right? Or 2 less than that, by less than that by an even number. So the first even number, just 2, so 2 minus 2, so it's either going to be 2 or 0, right? Now, the number of negative possible roots or zeros is going to be 1 in that case, right? And how many non-real complexes does it leave? None, right? Now, what if you have 0 for positive and we know we can have 1 for negative, right? So that means there must be what? 2 complex conjugates, right? Because we want to get to a total of what? 3 zeros. And that's how you handle a problem like that. So the function can have either 2 positive zeros, 1 negative 0, and no complex, non-real complex zeros, or it can have no positive zeros, 1 negative real 0, and these are all real, right? And then 2 complex conjugate non-real zeros, okay? So those are the possibilities using Descartes' law of basically signs. Give this one a try. See if you can come up with the table for it. All right, so again, the first thing we'll do is figure out what f of negative x is. So we get negative 8 times quantity negative x to the 4 plus 3 times quantity negative x cubed minus 4 times quantity negative x squared plus 5 times quantity negative x minus 12. In case you've missed it in my earlier videos, every time I say quantity, that means open parentheses, and as soon as I say an operation like to the 4 or something like that, that's when you close the parentheses. All right. So let's simplify it. So that's going to be negative 8. Negative x to the power of 4 is just going to be, since the negative is being raised to the power of 4, it's just going to become x to the 4. So x to the 4. Now, quantity negative x cubed, that's going to be negative x cubed. So times positive 3 will give me negative 3x cubed. This negative x, once we square that negative x, we get x squared times negative 4 will give us minus 4x squared. And 5 times negative x will be minus 5x and minus 12, okay? So number of sign changes in f of x and the number of sign changes in f of negative x. That's what we'd like to know. Now for f of x, notice from negative to positive, that's 1. Positive to negative, that's 2. Negative to positive, that's 3. Positive to negative, that's 4. How about the negative possible number of negative, maximum possible number of negative roots? Well, for f of negative x, negative to negative, no change, to negative, no change, to negative, no change, to negative, no change. They're all negative, so 0 sign changes. All right, so let's make our table. It'll be a little bit bigger this time because remember, the number of positive roots can either be this number 4 or less than that by an even integer, so 2, or again, you can go minus 4, which will give you 0. So all right, so don't forget, this time the number of possible positive roots is going to be 4, 2, or 0. How about negatives? That's easy. There's none. There are not going to be any negative roots possible, right? So now we want a total of how many roots? It's a fourth degree. It's a quartic polynomial. So how many roots do we expect? 4, right? So if you have 4 positive, that means these two, they're both going to be zeros because all the roots are spoken for by the positive reals, right? If you have 2 positive reals but no negative ones, that's going to leave 2 that are going to be forced where? Into the non-real category, right? And if you have no positive ones and no negative reals, that's going to make all 4 be what? Non-real. Just like that. Okay? So it's really not that bad once you get a hang of it. So make sure you understand these 2 examples before you move on. All right, so here's our very last problem, I promise. I wanted to show you this because it's kind of interesting. You look at the number 625 and that can be daunting, right? But I'll show you why it's not as bad as it looks. All right, so we know that if you want to find the complex zeros of this, we'll try the rational ones, and we know that the possible values for p over q, you know, the numerator value is p, so possible p values, those have to be factors of this number. So you can ignore the negative, doesn't matter, because we're going to take all positive negative ones anyway, right? So what are the factors of 625? Well, if we break down 625, right, in the way we've done before, what's the smallest prime number that will go into it? It's not going to be 3 because 7 and 2 is 5. 5 and 2 is 7 and 6 is 13. It's not divisible by 3, so it is 5. You divide it, you get 125 again. 5 goes into 125 25 times. Again, 5 goes into 25 5 times. And finally, 5 goes into itself once. So there's the prime factorization of 625. So basically, all the factors are going to be plus or minus 1, plus or minus 5, plus or minus 25, plus or minus 125, and of course plus or minus 625 itself, right? Now the q is nice, it's 1, right? So possible q values are just going to be plus or minus 1. So what are the possible p over q values? Well, exactly these. Because what happens when you take any of those and divide it by plus or minus 1? You get the same thing. So again, we just repeat those. Plus or minus 1, plus or minus 5, plus or minus 25, plus or minus 125, or plus or minus 625, right? So now we can go ahead and start by plugging in. Now you can almost look at this polynomial. This is what I wanted to bring to your attention, and realize that 1 is almost definitely not going to work, right? Just plug in 1. You know what happens? You get 1 minus 15 plus 80 minus 20 plus 375. The values are going up and down. There's no way these are going to combine to give you what? Something large enough as 625 so that this zeroes out, right? And for the similar reason, the same thing will happen with negative 1. Do go ahead and try it if you want. But personally, when I take a look at this, I'm going to go ahead and try 5 first. Okay, remember, you can try any one that you want. If you want to spend time on 1, you can. But I'm telling you kind of rationally why 1 would not be something to waste your time on. Okay, so we'll try 5. And the coefficients here are 1. Are there any missing terms? No. So 1, and it is in descending. So 1, negative 15, 80, negative 200, 375, and negative 625. Okay? Now the 1 drops down. 1 times 5 is 5, and negative 15 gives negative 10, times 5 is negative 50. Added to 80 gives 30, times 5 gives you 150. Combine those, you get negative 50. 5 times negative 50 is negative 250. Combine those, you get 125. 5 times 125 is 625. So we just hit a jackpot. Okay? Now when I look at these numbers, they do look to me like they may still play nice with 5. So I'm going to try 5 one more time. Remember, you can have a multiplicity higher than 1, right? So let's drop down 1. 5 times 1 is 5. That gives me negative 5. So 5 times negative 5 is 25. Notice how it's working out. It looks promising. All right, so 5 times 5 is 25, and negative 25. 5 times negative 25 is negative 125, and once again, we had another hit. Now, I look at these numbers again, and what looks promising? 5 looks promising again. I'm going to try it yet one more time. See, I wanted to give you a nice one before you go, so you have pleasant thoughts about the lecture. All right, so 5 times 1 is 5. 5 and negative 5 is 0. 5 times 0 is 0, and 5 gives you 5, and 5 times 5 is 25. So you get 0. All right, so once again, we hit another one. So we know 5 is a factor 3 times at least, or a 0 of multiplicity 3. Now remember, now I'm at the level where I have just a what? I have just a trinomial, x squared plus 0x minus 5, which is just x squared minus 5. I can abandon the process of the rational roots theorem, the remainder theorem, and move on to what? Just writing it out. So I get f of x is equal to quantity x minus 5, not once, not twice, but 3 times, right? And what's left is x squared minus 5, which is this trinomial here, okay? That quotient. So now all I gotta do is I gotta solve that, factor that. Now that's easy, because think of it like this. You can say x squared minus quantity square root of 5 squared, right? That's a difference of squares, isn't it? So it's just going to be x plus radical 5 times x minus radical 5. All right, so finally I get f of x Wait, I just scanned something. I guess I'm getting tired at this point too. You're not the only one. It's x squared plus 5. I have no idea why I put x squared minus 5. Let's go fix that. It's x squared plus 5. So when we come over here, it's not going to be that different from what I just did. But let me show you a little bit differently. Let me show you this way. Let's just say x squared plus 5 is 0. We're going to solve that to get the two factors, right? So we get x squared equals negative 5. So x equals what? Plus or minus square root of negative 5, which is plus or minus square root of 5 times square root of negative 1, which is going to be plus or minus square root of 5i. Okay? So, yeah, when we transfer this over, I put x squared minus 5 for some reason, and I'm sure it has to do with the length of this video, but it's supposed to be x squared plus 5. So we can get the factorization by finding the zeros of this polynomial. So now we're just going to say quantity x minus 5 cubed times x minus radical 5i times x minus negative radical 5i, which becomes plus radical 5i. All right, that's it. Okay, I know that was quite a bit of content, and you know, the good thing for you is, of course, you don't have to watch it all in one sitting. I did have to create it all in kind of one sitting, but you have the luxury of just like maybe watching half and then watch the another half another time. So I should have told you this at the beginning of the lesson, right? But anyway, I'm telling you now. Okay, so for future reference, if the videos are that long. But anyway, so I wanted to show you this because sometimes by just looking at a problem, you can eliminate some possible values. Or sometimes, one last thing I want to show you, and then I swear it's over. So what about you get something like this? F of x equals 5x to the 4 minus x cubed minus x squared plus x. Okay, you look at this, right? There is a particular zero that's screaming at you, and that you should never miss. What would that be? Look, they're all powers of x. So if x is what? 0, for example, that would be a very good 0 for such a problem. You see what I mean? So you would definitely want to start with trying 0, right? For a problem like that. So anyway, that should pretty much wrap it for the day. Long video, make sure that you spend some time with it, and we'll see you for the next one.